In this video, we will see the definition, examples, and the property of nilpotent transformation and also Lemma 6.5.1. Now, a transformation T from a vector space V to the same vector space is nilpotent. See, if T is a linear transformation on V, we say that T is a member of A of V. So T is nilpotent if T raised to K is 0, but T power K minus 1 is non-zero. That is, when you have the power of T to be some a number, positive number, which makes the transformation a zero transformation, but not for the lesser index, then you call that transformation to be a nilpotent transformation. So, as one of the examples, we have T from the collection of all ordered tuples, ordered pair rather, with the entries from the real numbers. So, T from R2 to R2 defined by any element here is an ordered pair. So let T take this element to x minus y in this ordered pair. If we have such a mapping, then this is definitely a linear transformation, and that is not checked here. It is a linear transformation. Then this is a nilpotent transformation. The reason is when you apply this transformation T to this element xy, once you get x minus y, and when you apply this again, so it will be um, the transformation T takes this element. How the transformation is defined? It is the difference of these two. So you have the difference of these two, x minus y, you have to find the difference. Put the same thing in the second component also. So this is what you have. So this gives, you have your x minus y, here minus into minus plus, so these two will get cancelled, x minus x, so get 0, in the same way 0. So it is the transformation T square that vanishes. So we can also say like this, xy operated by T square is xy is same as operated by the zero transformation. As the images are equal, the mappings must be equal. So you get T square to be the transformation 0. So you have this definition being verified. So T to be a linear transformation that we have. And in the same way in uh, V, if it is R3, when you define the transformation tree in this way, when you define the mapping in this way, that becomes a linear transformation. And this is a nilpotent transformation. Again, the same explanation. When you apply once, this is what you get. Again, twice, then 3 times only. When you apply, you get this. So, checking that may be somewhat difficult. So, the transformation, we know that given a transformation, with that a matrix can be associated. So, in this case, the matrix would be 1 minus 1, 1 minus 1. This 1 minus 1, 1 minus 1. And in the same way here, when we try to write the matrix of T, it will be, you have matrix of T is 1 minus 1, 1, 1 minus 1, 1, 1 minus 1, 0. This is the matrix of T. Of course, we have considered the standard basis. So that doesn't matter. We want to have the matrix of the transformation. And this, when you suppose you take this as A, you will get A cube to be the null matrix 0. So when the matrix is nilpotent, corresponding transformation will be nilpotent, because we know that with every transformation we can always associate a matrix, and given a matrix A, with that a transformation can be associated. So because of that, because this is nilpotent, A is nilpotent, so this transformation should also be nilpotent. So that is easy way of checking whether the transmission is nilpotent or not. Then this property of the characteristic roots of a nilpotent transmission. You only have the characteristic roots value to be 0. It is not a non-zero quantity. So for that, you consider T to be a nilpotent transmission with the index of nilpotence. This power the index is called the index of nilpotence. So suppose I have this to be nilpotent with index of nilpotence k, that is T power k 0, T power k minus 1 non-zero. Let lambda be a characteristic root of T. Then we have a non-zero eigenvector with Vt equal to lambda v. Now you consider Vt square. It is Vt t, but Vt is lambda v. So you have lambda v t being a linear transmission. You have this, and again you have Vt to be lambda v. So you get this to be lambda square v. So Vt square is lambda square v. And proceeding like this, you will get Vt cube to be lambda cube v, and so on. Vt power k to be lambda per k v. But what we have is T power k to be zero transmission. So V zero transmission lambda per k v. But zero transmission takes any vector to vector 0. So lambda per k v is 0. This is scalar, this is vector 0. This is also vector, and in which small v is non-zero. This vector is non-zero. So you need to have your lambda k to be 0. So you get from here lambda to be 0. So characteristic root lambda was assumed to be a characteristic root of t, and that happens to be 0. So characteristic roots of a nilpotent transmission are only 0. Next we have this lemma 6.5.1. This lemma is very basic in proving the fundamental theorem on nilpotent transmission or Jordan form, or even the last one, CRT, that is a rational canonical form. You have even for that your this lemma is very much needed. So the proof of this is to be followed carefully, and it is very simple also, and the statement needs to be mentioned in all the fundamental theorems. When that is proved, this must be mentioned. So the statement goes like this: if V is the direct sum of V1, V2, and so on Vk, where Vi is a subspaces of V of dimension Ni, that is V1 is a subspace of V, its dimension is N1, V2 subspace of V, its dimension N2, and so on Vk subspace of V of dimension Nk. So each of them are given to be invariant subspaces under the transmission T. Then what is true is there exists a basis of A in which matrix of T is of this form, where each AI is a matrix of order Ni cross Ni induced by T on Vi. See, we know from section 6.4 that whenever W is invariant under T, T will induce a linear transmission. So whether you consider V mod W, you have another vector space on which whenever you have T to be V that W to be invariant under T, you can always talk about the another mapping. So in this case, what is that we consider is the restriction mapping. T restricted to that subspace. So that will be the induced transmission. So where each AI, so that is what is mentioned here. AI is a matrix of order Ni cross Ni induced by T on Vi. So it is the transmission induced whenever you have subspace invariant under T means it will induce. So whenever you have invariant, there you will have the word induce. So invariant under T, and here that will induce a linear transformation. And from this nilpotent transformation onwards, that is whether it is nilpotent, Jordan, or rational canonical form, you will have to have the induced transformation as the restriction mapping. T restricted to Vi will be that induced transformation whenever Vi is invariant under T. So we establish this, or rather we will give the proof of this lemma by considering dimension of V to be 5, and let it have subspaces say V1 and V2 of dimensions say 3 and 2. So these are our assumptions only. So we are because it will be easy for you to understand the lemma with the help of numbers rather than n1, n2, n like that. So we have taken dimension of V, which in the theorem will be assumed as n, and V1 will be of dimension n1, n2, and so on in the actual proof. But to understand the proof easily, we have got dimension of V1 to be say 3 and V2 to be of dimension 2. Now, because V1 is of dimension 3, we can have a basis, 3 elements in the basis. So we shall take them as V1, V2, V3. And even for V2, which is of dimension 2, two basis element we should have V1 and V2. But we cannot use the same letters. So we superfix. For the first one, we superfix with 1. And for the second one, we superfix with that the number 2. So according to our assumption in the lemma, V must be direct sum. So that's what we have written. What are V1 and V2? They are subspaces of V invariant under T. All these are our assumption. And here particularly we have taken dimension of V to be 5 and V1 to be of dimension 3 and this one V2 to be of dimension 2. Now because dimension is 3, it will have basis elements with the basis will with 3 elements. Superfix that with 1 because of suffix 1. Superfix with 2 because of the suffix 2. Right. Now T being invariant under T, V1 and V2 are invariant under T, it will induce a linear transformation. That is our restriction mapping, I said already. T restricted to V1, we call it as T1. T restricted to V2, we call it as T2. So you have V direct sum of V1 and V2. T is the linear transformation which acts on. T is a linear transformation which acts on V. So it is from V to V. We are having the basis for these 3 elements, basis for these 2 elements. So altogether you have 5 elements. They will form a basis of capital B whose dimension is 5. So 5 basis elements, dimension 5. Now T restricted to V1, we call it as T1. T restricted to V2, we call it as T2. Now given, see we know that we said already that given the transformation, with that a matrix can always be associated, and for which of course we must know basis. What is the basis? So here I have T1 and I have got the basis elements as this. So I can talk about the matrix of T1. So matrix of T1 we are going to denote it as say A1. Matrix of T1 we are going to denote it as A1. So let M of T1 in this basis be A1 and in matrix of T2 in this basis is A2. So what will be A1? We shall name it as it should be 3 cross 3 because dimension is 3, it should be 3 cross 3. And here dimension 2, so the corresponding matrix should be of order 2 cross 2. So we have basis elements. Whatever basis that you have, the same thing should also come here. So that is known to us. So T1 on this basis, I have a transformation, I have basis, so I'm going to have the matrix. So these are the coefficients we consider here. So alpha 1 1, alpha 1 2, alpha 1 3 basis elements, linear combination. And again in this case you have basis elements, again you have this and the linear combination. Similarly the last one. So A1 is this matrix, and how did we get that? Because of this only we have got that. And similarly for A2, basis elements only two that we have for V2. On that you have to restrict it to V2, that is your T2. So you have the corresponding linear combination being given by this, and so the matrix will be like this. So we have got A1 and A2. So these are basis elements of V1, these are basis elements of V2. Now what we need is matrix of T, right? So that means we need to now combine these bases of capital V1 and the basis of capital V1 and basis of V2. So together we have 5 basis elements, that's for capital V. So we have the union of the basis of V1 and V2, namely this will be a basis of V, will be a basis of V. Therefore the matrix of T in the above basis. Now this is the basis now that we have. So basis whatever you have here, you should write the same thing should come here also. That is the rule to obtain the matrix of T. So you have V1, all these are already written, but remember these basis elements should also come there, but we don't have them. When we wrote this we don't have V1 superfix 2, V2 superfix 2, but when we write it for this is T1 actually. We have this is T1. Sorry, this is T1 on V1 is nothing but T. It is T. It is also T. This is T. That's correct. So V1 superfix 1 on V1 it is taken as T1. This T takes the avatar of T1 on V1. Right, so restriction mapping, so this is how it should come, right? So now these are now the members of capital V. On capital V you have the linear transformation. So now you have this T, these being a member of V1, T restricted to V1 we must have, that is denoted as T1. So you have this step, and for this we know already what is this linear combination, and these bases are not there, so but they must be written here, so we supply with scalar 0. And similarly for this one, when you come to the next one, this is a member of V2. So only T will act on this when it is T2. So you have as for V2 is concerned, you don't have these. So you have to have 0 0 0. And so this one we have already written, that is what we have written again. So now when you write the matrix of T, it is first row, second row, third row. So that is what is written here. So we have this already, we have denoted as this one as A1 and this one as A2, and this is null matrix. We know that null matrix can take any order. So 0 null matrix, this is also null matrix. So matrix of T in this basis, this is the basis of capital V. So you have matrix to be this. Now the same thing is now explained for the general case, namely dimension of V1 is N1, dimension of V2 N2, and so on, dimension of Vk Nk. So the basis elements will have N1 elements, N2 elements, and so on Nk elements. So accordingly, when we combine all the basis elements of capital V1, V2, and so on capital Vk, we will get the basis of capital V. And so matrix of T in that basis when we write, it will be A1, A2, etc. Ak, where each Ai will be the matrix of Ti in the corresponding basis. So you have Since V1 is invariant under T induces a linear transformation T restricted to V1, that is T1 on V1, such that the matrix of T1 in this basis suffix 1 of V1 is A1, and that is of order N1 cross N1. And since V2 is invariant under T induces a linear transformation T2 on V2, such that the matrix of T2 in the basis this of V2 is A2 of order N2 cross N2. So here we can also mention let dimension of V, we can mention let dimension of V be N to have more clarity, and let dimension of V1 to be say N1, dimension of V2 N2, and so on, dimension of Vk Nk, so that this will be meaningful. Of order N1 cross N1 and so on, you are having N2 cross N2, and in general Nk cross Nk for the last one. Now since V is the direct sum of this, the union of all these bases will form a basis of capital V. So as we did in the previous case, all the basis elements should come here, and the first few will be basis of V1. So that is why T will now become T1, T restricted to. And then for the second, T2 it will be same T only, but when it acts on V1, it will take the avatar T1. This avatar up to this, then takes the avatar T2 and so on, TK finally. So these T2 will have effect only on V2 elements, and this TK it will have effect only on the elements of capital VK, and T1 will have action only on capital V1 elements. So for how about the rest? It will not act. So when it doesn't act, we will supply them with 0 only. That is the natural process. So you have this. So when you write this in the matrix form, this is what you get. Matrix of T in the entire basis should be of this form. A1, A2, etc. Ek, where each AI is an Ni cross Ni matrix. The rest 0 stands for null matrices. They need not be of the same order. Null matrix can be a rectangular matrix. So this is the proof of this lemma, and that is very important in the sense that in the um, basic theorems in all the three sections, Jordan form, rational canonical form, nilpotent form, this lemma is very, very important. So that must be mentioned. Let me repeat the statement. V is the direct sum of V1, V2, Vk must be given to you. You must know that. And what should be known about VIs? They must be subspaces, and dimension we'll take them as say Ni, and invariant subspace, invariant direct sum. So you need to have V to be the direct sum. V should be the direct sum, and Vi should be subspaces, invariant. Then it will in invariant, when it comes, you must have the word induce. Invariant, whenever it comes, you must see to it that you are writing induces. So you have these AIs to be the matrix induced by T on Vi. That is what is denoted as Ti. T restricted to Vi is denoted as this. So you must have direct sum, invariant, um, subspace, of course, subspace. So DSI, it should be direct sum. Which should be direct sum? V should be direct sum of what? Subspaces. What kind of subspaces? They should be invariant subspaces. So if only these are true, then you will have. This is for you to understand the lemma. These numbers are considered. So this is only for you to understand. And in the examination, if the proof is asked, only this proof needs to be given, not the one what is explained here in this blackboard. This is for you to understand, that's given. So finally you have the matrix like this. So V should be direct sum, and then direct sum of subspaces. Okay, so subspaces, and we must have the subspaces to be invariant. Then you can find a basis of V in which matrix of T is of this form. Thank you.